Begini. Banyak di sini. Share, screen, dua. Begini. Screen dua kan? Screen dua kan? Screen dua kan? Screen dua. Mana sih?
Okay, hello ladies and gentlemen. We're starting the event now. Welcome to the IC technical meeting the Great Infrastructure Challenge, Advancing Remote Monitoring with Satellite Technology. This event is brought to you by the Institution of Civil Engineers and supported by Multibangun. My name is Rifa, so hello everyone. And it is a pleasure to act as your master ceremony in this event. Before we start, allow me to read the rundown of our event this evening. So I'm going to read the rules of the webinar and also the event here. And then second, there will be a short presentation by a Bina Nusantara University student, Alessandro Prinskana. And then the event later will be handed to our moderator, Michael Dobby of ICE, to start the session of our main speaker, Dr. Andrew Lees from GeoFam. The session will be later continued to a Q&A session. So ladies and gentlemen, for your own convenience, please put attention to the following rules. You can submit your questions to the speaker through the Q&A feature for those who are attending online. It's located at the bottom of your screen and the question should be in English. For those who are here, you can raise your hand later at the Q&A session and then the moderator will let you speak and then you can address your questions. So you can raise your questions, especially for those attending online, before, during, and after the presentation of the speaker. Okay, now without further ado, I would like to invite today's student presenter from Bina Nusantara University, Alessandro Prinskana, to give his presentation. To Alessandro, the time is yours. Jadi, this your mic, ya? Di laptop dulu.
Good evening, ladies and gentlemen. My name is Alessandro Prinskana, and I'm a Bachelor of Civil Engineering from Binus University. I would like to make a brief presentation about my final thesis. The title is Utilization of QGIS and HAC Models for Spatial Prediction of Inundation Extent in the Sub-Watershed Area of Kali Krukut. I'm supervised by Ms. Julia Astuti, a lecturer from Binus University. Here are my research backgrounds. There are 5 main backgrounds. First of all is urban flood in Jakarta. And then the second one is high rain seasons on Jakarta. Third one is flood impact. The fourth one is land use change. And the last one is a need for spatial analysis in the land of Jakarta. Here are a few problems encountering my research. First of all is the spatial modeling. And then there's hydrologic analysis. and then the flood in the nation area, and then last one is integrated prediction. For my purpose, there are four main purposes of my research. The first one is I need to model the sub-watershed of Kali Krukut using software like QGIS, HKMS, and HKRAS. And then the second one, I can analyze hydrological characteristics and design flood discharge from Kali Krukut. The third one is to assess the shape and extent of flood in the nation. And the last one is to map flood distribution spatially and estimate the flood area surrounding Jakarta. Here are my scope of research. First of all, my research is based on Kali Krukut, focusing on areas near Bendungan Hilir and Mampang area. And then I use BMKG rainfall data ranging around 2000 and 2020. And then I use the flood discharge for the return period of 5 years to 25. And then land use included without thematic historical analysis. And then visual observation indicates river narrowing. And then I did not include sediment analysis. And of course, socioeconomic, infrastructure, and mitigation scenarios. And then my hydrologic analysis is based on the Indonesian National Standard, or we used to call SNE 2415 and 2016. Here are the analysis. The first one is we must know the rainfall frequency analysis, and I use the BMKG data. And then the second one is dam acquisition for hydrologic modeling. I use the dam for creating the area surrounding Kali Krukut. And then the third one is I create boundaries for the sub-watershed from the Bendungan Hilir and Mampang. And then next, I process hydrology modeling using the QGIS. And then next one, I calculate the flow. And then the last one, I map the flood simulation. Here are the process. My flow chart, the first one is problem identification. And then I collect the data. And then I use the dam and sub-watershed delineation to find the area. And then for hydraulical analysis, I have two steps. First one is discharge estimation in HKMS software, and then base map in QGIS analysis. And then lastly, we have a flood Indonesian mapping using HKRAS. And then lastly, we have the conclusion. Here are my results. As you can see, there are 4 pictures. Each return period, the flood in the nation area is getting larger. For return period of 5 years is around 0.9 square kilometers. And then for 10 years is 1 square kilometers. For 20 years is 1.2 square kilometers. And for the 25th year is 1.3 square kilometers. And this is the water depth of each return period. And then here are some of the conclusions that I got from my research, including the curve number, the mesh size, and then the hydraulical characteristics and modeling results. Here is the peak discharge. As you can see, for each return period, it gets larger and larger. And here are some software limitations that I got from using these 3 softwares. For each software, I have difficulties. The first one is for QGIS. There is no built-in hydraulic modeling, and then we need to manually input the data for export and conversion. And then the analysis accuracy, of course, depends on my input. And the next for HKMS software is I cannot model the detailed geometry of the river, and then it's very highly sensitive to input parameter accuracy. And then it's less effective for small-scale urban areas, especially in my research. And then for the HKRAS software, it requires a high-resolution topographic data when using it, and then less optimal using in urban environments. And then the 2D mode usage is very complex and very technical. That is all for today. Thank you very much for listening. And I wish you a happy evening today. Thank you.
Thank you, Alessandro. So thank you, Alessandro, for your excellent presentation. If you're interested in the topic that Alessandro just presented to you, please do approach him. He will be happy to answer your questions and talk about it. So Now, for the next session, this webinar will be guided by our moderator, Michael Dobby. Before I give the floor to Pak Michael Dobby, I would like to remind you that you can start submitting your questions from now, during and after the presentations for those who are attending online by using the Q&A feature. And then for those who are here, you can ask the presenter about the presentation later at the Q&A session. So without further ado, Pak Mike, the time is yours.
Okay, thank you very much, Rifa. First of all, welcome to everybody to this evening, which is organized by the Jakarta Local Association of the ICE. It's good to see a growing crowd of people here. And I think this is about our 4th or 5th event this year. And we have 1 or 2 more that we're planning to do as well. But today, in our normal style, we've been very lucky to have a short presentation from a BINUS student. Alessandro, thank you very much. You presented very clearly. And I think you require some questions, actually. Yeah, I think if anybody wants to ask Alessandro some questions later on, then we'll find some time to do that, because I thought we don't give him very long. We don't give him very long to present, and he kept inside his time extremely well. And I think there was a lot of interesting content there that people might like to learn about, especially when I see David Mee over here, who I'm sure have a few questions about things like that. So would I be right, David? Oh, he's late. He's late anyhow. Okay, well, so thank you again. Very nice indeed. Thank you. Yeah, one more round of applause, please. So now it's my pleasure to introduce the main talk tonight. First of all, I'm going to welcome a colleague of mine, Dr. Andrew Lees. We've been colleagues for 10 years or so. Andrew is from the UK originally, and he studied at the University of Southampton, where he did both bachelor's and degree and PhD. And he has particularly specialty in the area of numerical analysis, finite element analysis and things like that. But also, a little while later, he founded a company called Geofem to provide services to the industry, civil engineering industry, specialized services, initially mainly in that same area of numerical analysis, but then decided that they could expand what they offered and their expertise into the area of using satellite data to look at things like deformation of the ground, and you'll hear much more about it from Andrew, but it's absolutely fascinating what can be done now with satellite information. I think we all think, well, satellites are such a long way up. How can they actually tell us what's going on to a few millimeters accuracy down here? That's inevitably a very good question. And I think Andrew might explain to you in a minute how that is possible. I've been lucky to learn quite a lot more about these techniques over the last days especially, and a little bit before that. But it is, I think, a really interesting additional contribution, if you like, to the way we analyze the ground and the land around us. Those of you who are geotechnical engineers like me, we're always very keen to know what's happening with our structures. Are things deforming? How fast are they deforming? And things like that. And with this technology called INSAR, we have a way of doing exactly that. And I think for me anyhow, I think it's a really fascinating technique. And I'm going to stop talking now, otherwise I'm going to go on for far too long. But I'd like to ask Andrew, please, to take the stage and explain to us how you can measure millimeter deformations from a satellite. There's an awful long way up in the... Okay, Andrew, please.
Well, thank you very much, Mike, for that kind introduction. Thank you everyone in the room for coming, and thank you for those online who've tuned in. I've watched a few of these events online, And this is the first time I've been in person, and it is truly a unique venue for an ICE event, I must admit. So for any of you watching online, if you are ever in Jakarta, be sure to come here and enjoy the event in person. You'll be assured of a good time and a long evening, I think, here. So, yes, thank you to the ICE, Local Association, for the invitation to talk to you about this new technology to help meet the great infrastructure challenge that we are facing. So what do we mean by the great infrastructure challenge? Well, we have a lot of legacy infrastructure that is aging. So it is experiencing heavier use than ever. And many stakeholders and owners of this infrastructure are dealing with declining budgets or insufficient budgets to deal with all this aging infrastructure. And on top of all that, we're facing the added challenge of climate change. So our infrastructure is getting older and developing defects that we need to be looking for. It's being used more heavily than ever, and it is experiencing worse climatic conditions than it was ever intended for and it has experienced in the past. So all these together, plus on top of all that, the shortage of skilled engineers to manage, maintain this infrastructure. So this is what we mean by the great infrastructure challenge, this multitude of different issues that it's currently facing. Geohazards are also a particular issue and challenge for infrastructure. Geohazards include things like coastal erosion, the landslides, sinkholes, and clay subsidence. And you can see estimated costs of those indicated on the diagram there. And due to climate change, quoting the World Bank here, geohazards are difficult to manage and the numbers are continuing to increase with climate change. So moisture is a very important parameter in the triggering of geohazards. And increasing climate or increasing weather extremes due to climate change means extremes of moisture within the ground, and that can lead to triggering of some of these geohazards. So that's something we need to be monitoring and keeping an eye on as weather conditions become more extreme. The big problem with geohazards is they can occur almost anywhere. So we have thousands of kilometers of road and rail and other infrastructure networks and whole cities to be monitoring, but we don't know where the geohazards could occur. The result of that is maintenance is often reactive. So too many times a landslide occurs, it takes out the infrastructure, so that causes weeks of disruption while the infrastructure is not available. The repair has to be immediate and reactive. It's not properly planned. And that becomes a very expensive way of maintaining infrastructure. With climate change, that means the resilience is becoming very low because the maintenance is very reactive. The disruption is only going to get worse as the weather extremes increase. So how are we going to monitor these thousands of kilometers of infrastructure given the shortage of skilled labor and all the challenges that it faces? So that's the problem that I hope in some way can be addressed by new technology such as satellite monitoring. So I intend to show to you today how we can determine important parameters to help predict geohazard occurrence from data from geospatial data from satellites. So we'll see how we can determine surface soil moisture content to try to predict those triggers of geohazards, and how we can measure displacements to see the early signs of these geohazards before they become a major failure mechanism. And we'll see how we combine this data with other sources for geohazard susceptibility assessment. And then I'll show some examples of improved geotechnical insight gained from satellite data. Now, the measurement of displacement and soil moisture by satellite has come about due to something that I call the SAR satellite revolution. I expect you're all familiar with optical satellites, such as in the Google Maps view. You can select the satellite view. That will give you an image that you can interpret with the naked eye. SAR satellites are something very different, not something you can view with the naked eye. It's something that needs to be processed. So what does SAR stand for? It stands for synthetic aperture radar. The terms synthetic and aperture are technical terms related to how the satellite can improve spatial resolution. But for our purposes, we can think of it in terms of radar, just like radar on the ground surface to detect shipping and aircraft. This is radar, but it's mounted on a satellite. So it's an active system that emits an electromagnetic pulse, and it detects reflections or backscatter from objects on the Earth's surface. And it is from that backscatter that various parameters can be determined. A big advantage of SAR is the portions of the electromagnetic spectrum where it operates. That's microwave and radio wave portions. That means it's unaffected by cloud cover. So that's particularly important in areas such as where we are in Indonesia, where cloud cover is frequent. So optical satellite data is not much use when it's a cloudy day, but SAR data can penetrate the clouds and is unaffected by those weather conditions. And it can also operate day and night. So it's a very reliable source of data. Each time the satellite passes every few days, we are 99% sure, more or less, that we are going to get data. So what do they record? From that backscatter, there are two main parameters that are measured. One is the amplitude of the backscatter. That depends on a number of factors regarding the textures of the Earth's surface. One of the factors that affects amplitude is the dielectric constant of the ground. And dielectric constant is related to soil moisture content. So that gives you a clue as to how we can derive soil moisture content from SAR images. The other main parameter that is measured is the phase of the received backscatter. And if a difference is detected between successive images, that can be processed into displacement. So let's look at the displacement measurement in more detail. So in simple terms, if you imagine a satellite here that emits its electromagnetic pulse, and it receives backscatter from various objects on the Earth's surface. Let's imagine it's that building, and we get the blue line reflected on the first pass of the satellite. Then the satellite continues on its orbit and returns next time it passes over and emits the same pulse and receives backscatter. Let's imagine it's the red line this time from the same object. But in between the two passes, the object has moved. Therefore, there has been displacement. Now, rather than measure the distance from the satellite all the way to the object, the way the satellite detects the movement is by detecting a change in the phase of the backscatter. So with the wavelength being a few centimeters, if you can detect a fraction of that phase, you are already detecting displacements of about sub-centimeter level. The next stage is to analyze a time series of images, at least about 20 SAR images in a time series sequence. And by looking at them all together, you are able to reduce some of the sources of error even more, and you can get the accuracy of displacement down to about 2 to 4 millimeters. So it's a very accurate displacement measurement, but over a relatively large spatial resolution. So the free Sentinel-1 data of the European Space Agency has a spatial resolution on average of about 10 meters. So you are getting very precise displacement, but averaged out or coming from locations within each pixel. So because of the relatively large spatial resolution, it's very suited to monitoring large objects, such as whole infrastructure networks. So you're getting very accurate displacement that will indicate the early stages of a landslide, for example, but over relatively large areas. So it's not going to give you displacement at specific points. It's going to give you displacements averaged over the pixel size of the satellite data. Let's look at some examples. So this is how INSAR displacement data is often presented. So we get a lot of data, and that makes it suited to displaying on a GIS platform. So the data is normally presented in this form, overlaid on an optical satellite image so that you can see where the points relate to. So the optical satellite image is shown, but remember that the displacement data comes from a different satellite image, from a SAR satellite image. The different colors indicate the rates of displacement. So green colors indicate no significant displacements. Oranges and reds, movement away from the satellite, which is often associated with subsidence, possibly downslope movements, and blue colors, movement towards the satellite. So here, data is displayed along a wide rail corridor. The railway line is easy to see. That's that line of colored points because a rail line provides a very coherent data, lots of sources of reflection of the radar data due to the rail, the sleepers, the ballast, and so on. Elsewhere, you see clusters around towns and villages, so you get very good data in built-up areas. In more rural areas, the data may be more patchy. Certainly in agricultural areas where crops are growing and being harvested, that means textures are changing all the time, and it is more difficult to obtain displacement data. So you may see some gaps in the data, such as shown here. But you can see the big advantage of INSAR is being able to obtain displacement across large areas. So along this rail network, you can quickly see areas that are experiencing more movement than others. And that could signify potential problem areas. So on a GIS platform, you can zoom into the data and click on any of the points to look at the accumulation of displacement from the start of the analysis through the entire period that's been analyzed. And you can compare some locations with other locations nearby, such as that. Just to put the different movements in context with other locations. So it's a very quick way of looking at problem areas. I see it as a screening tool. This data is not going to give you all the answers. If you see movement somewhere along a rail line, that's an area for further investigation. You're not going to be able to fully identify the cause or design the remedial measures based on this data alone, but it is extremely useful for covering large areas and pinpointing those problem areas that you may not be aware of. And And at those, you can focus more resources to do some specific site inspections or do some site-specific surveys in situ or install some in situ sensors. I would never propose this satellite data as an alternative to other methods of monitoring. It has the greatest value of covering large areas and screening, and then can be complemented by other methods of measurement that can be focused in those problem areas. Now, here's a good example to show the value of this screening use of satellite data. So this is Carola Bridge in Dresden, Germany. It had two bridges adjacent to each other, one a road and one for light rail that you see there. Unexpectedly, about a year ago, the rail bridge collapsed. And it collapsed without any warning, fortunately at night, so there were no casualties. But it does raise questions about the resilience of aging infrastructure. This bridge was quite old and clearly had developed a fault that had gone undetected. So a good way to screen bridges across large area and other items of infrastructure is by satellite. So here we have an optical satellite view of the city of Dresden. And the middle of the three bridges is the one that we're interested in. So I'm going to display the INSAR displacement data for a period of 2 years prior to the collapse. And we can see mostly green colors in the other two bridges, but clearly yellows and oranges, an indication of an issue. And since this is movement away from the satellite, possible sagging of the bridge of only a few millimeters over 2 years, but enough of a contrast against the other bridges to understand that there was a problem with this bridge. Now, we couldn't have predicted the collapse from this data, but had this data been available and used prior to the collapse, there was enough information there certainly to warrant an additional investigation, maybe installation of some sensors on the bridge or some detailed surveys in situ to try to identify what the problem was, possibly to even remediate and repair the problem before the collapse, or at least to have closed the bridge to avoid the risk of any casualties had that collapse happened during the day. Now, here's another example of monitoring a structure, this time a relatively new one. This is a reinforced soil wall. This was part of a repair to a landslide to this road that goes to quite a popular tourist attraction at Panhala Fort in Maharashtra in India. It's a relatively large structure, something that is suited to monitoring by satellite. In this case, it was soon after construction, just to check the satisfactory performance of the structure. So here's an optical image from overhead, and on top of that is plotted INSAR displacement data. So we can see mostly green points. We can select a number of those points for plotting, and we see some noise that we expect due to some sources of error, maybe thermal movements or some shrinkage and swelling of the ground due to different moisture conditions, but overall, no accumulation of displacement. So it's a good indicator of the health of that structure during that analysis period. Everything seems to be fine. But an interesting aspect of using satellite data is it does cover a large area. We tend to select a minimum size of a few kilometers across. So the retaining wall is right in the center of that area, but it gives you a lot of data from the surrounding area. And as we gradually zoom in, we saw that the retaining wall was doing okay, which is what the main purpose of the analysis was, but we can't help looking elsewhere, and you start to see patches of yellow and orange. So you start to wonder what's going on there. Just your own curiosity you can't help it. So we saw this area here experiencing some movement around that area of housing there. So as a sort of duty of care, we do point that out as part of our work, and this was you may like to have a look at that other area there. Capabilities of this technology. Perhaps you can take action to investigate further. Oh, and we plotted some of the values there, and you can see, in contrast to the retaining wall, a gradual accumulation of movement there over just over a year. So a reason to investigate that area further. Here's another example where we were monitoring a rail line in an area of, in a fault zone area, an area with an active fault. This is a rail line in the Konya area of Turkey. So immediately you can see movement around the active fault. So a very good tool is satellite data and INSAR displacement for monitoring the movement along fault lines. So the rail line is going from the bottom left diagonally up to the middle at the top. And you can see no significant movement over on the west side of the image. But as you go over to the east side, you can see oranges and then reds indicating rates of displacement up to 30 millimeters per year. So a good method for monitoring movement of active faults. Now here we have a tailings dam example. INSAR displacement monitoring is quite often used already and has been for a number of years for monitoring tailings dams, because tailings dams can be susceptible to collapse. This is an infamous example, Jagersfontein tailings dam in South Africa that collapsed in September 2022. And you can see the breaches of the dam down the bottom right and in the middle, which unfortunately led to the tailings escaping into the local environment, causing some deaths locally and a lot of environmental damage. So these examples are looked at to try to demonstrate the value of the satellite data in trying to prevent these collapses. So this is showing displacement data prior to the collapse, so a month, in years before the collapse, showing movement just in that corner where the breaches occurred. So there were definitely the warning signs available there from satellite data to investigate further and to possibly have avoided that collapse had avoiding action being taken. So here we plotted displacement data from INSAR around the whole perimeter of the tailings dam. So the area between the vertical lines is that area where the breach occurred. And we can see in the two graphs on the right how significant movements were occurring just at that location for well over a year before the collapse. So had the tailings dam being monitored with INSAR, it would have been clearly highlighted to the owners that there was an issue in that area of the tailings dam. The only time when there was not movement was in the period in the left-hand graph where mining operations did cease for a period due to COVID. So a commonly asked question is, have these techniques been validated? So 2 to 4 millimeter accuracy of INSAR displacement is all very well, but where's the evidence for the accuracy? Well, in the early days of INSAR monitoring, the European Space Agency funded the Terra Firma project in 2009, which used SAR data from rural and urban sites in the Netherlands and compared the ground truth data of displacement against INSAR and found standard deviations of only about 1 to 1.8 millimeters per year. And that report is in the public domain. As we do our work as geotechnical engineers ourselves, we often have the opportunity to compare our data from satellite with data that comes from in situ measurement. So in this example of monitoring long-wall mining subsidence in New South Wales, Australia, this picture shows a heat map, if you like, or a contour plot of subsidence that was detected by satellite. And that coincides with the blue hatching, indicating areas where long-wall mining was being undertaken at the time. Now, it is a legal requirement to undertake subsidence monitoring at long-wall mining operations in New South Wales. So we were able to compare the weekly in situ survey data shown in the upper graph along Camden Road, where the green lines show the vertical displacement week after week, leading to the final bold line shown there along the road. We have compared that directly with the INSAR displacement data on a regular basis, building up to the final bold line that you see there. And the final result agrees very well with the weekly in situ survey data, and certainly within the survey tolerance of plus or minus 15 millimeters. Here's an interesting example from an area of expansive clays. Now, road networks and expansive clay areas suffer the perennial problem of cyclic shrink and swell, which leads to movement along the edges of the road, eventually to longitudinal cracking. They get repaired, maybe the road even resurfaced, and then the longitudinal cracks just return. So as part of a trial with the University of Texas at Austin and Tensar, different solution methods were being tried in this area, and this is showing the displacement of the road network before the remedial measures were installed. We filtered out the data from the building, so it just shows the data along the road. What's interesting about this is the whole image shows the same geological unit, the same expansive clay. So by conventional means, this would have the same susceptibility to expansive clays across the whole area. But you see in reality, there's quite a lot of variation in the movement in different areas. So there can be much more precision about assessing susceptibility to expansive clays by looking at patterns of displacement, as well as soil moisture that we could look at too. It's interesting to see that the main road along the bottom of the image and on the right-hand side going upwards, they're green colors there because they are main roads and larger buildings built to a higher standard, whereas the residential streets in the middle of the image, they're the ones that are really suffering from the movement damage. And it was in some of those roads that the trial was undertaken. So we can plot the data from some of those points. And if you use the right processing techniques of the SAR data, it is possible to get non-linear plots showing the seasonal cycle of movement. So we've plotted 2 points in the residential area, showing both seasonal movement and a gradual ratcheting of subsidence, compared with the green line, which is a point from the main road that was not showing significant movement. So that's a very good method for covering large areas to assess susceptibility to expansive clays. Now, I just want to move on to another parameter that we can determine from SAR data, which is soil moisture content. As I mentioned earlier, the amplitude of the backscatter received in a SAR image can be related to soil moisture. And with the benefit of some additional data to help adjust that, we developed an algorithm using machine learning that studied a worldwide database of in situ soil moisture measurement available from climatic zones and geological conditions all over the world. That data is available publicly. And we looked at over 3 years of data and compared that with the satellite data from multiple sources, including SAR amplitude data, and developed an algorithm that can estimate the moisture content at the surface where there is exposed ground or light vegetation with an accuracy with an R² value of 0.81. Now, this is particularly valuable because most geohazards are triggered by raised moisture conditions. So if we can detect raised moisture conditions, that is giving us a good indicator of the susceptibility to geohazards and possibly the opportunity to intervene and address those raised moisture levels before they develop into something serious. But to illustrate how the soil moisture algorithm works, I'm going to use an example from Auckland here, and an example that's more relevant to Alessandro's talk beforehand, because this data was used for flood prediction modeling, not directly a geotechnical application, because an important input parameter to flood prediction modeling is the saturation level of the ground. More saturated ground would mean faster runoff and faster rising flood levels. To help provide this data, Auckland Council had installed about a dozen soil moisture sensors across the Auckland area, but that still left rather large gaps in between. And that's where we were able to provide soil moisture data, such as this, from free Sentinel-1 data. So on an average 10-meter pixel size, we were able to provide soil moisture data at the surface, and we're comparing the dry season on the left with the wet season on the right. Because there were in situ soil moisture sensors, we were able to compare our satellite data with the in situ data. So the in situ data, one of the sensors is shown in black over about 7 years, and you can clearly see the seasonal cycle between summer and winter, apart from late 22 and 23, where they had some severe typhoons that upset that seasonal cycle. Now, with the global algorithm based on the global database, that is shown in red and is shown to provide a reasonable agreement with the in situ measured data. But because the algorithm is derived by machine learning, you can give it the local data of the in situ soil moisture sensors and further train the algorithm for local conditions. So once we had done that, we had the blue line, which matched even more closely with the local data. So that's a good example of how this algorithm works, how with the benefit of working in conjunction with in situ data, it is possible to improve the accuracy even further. Next, I want to show an example where we can use soil moisture data to help inform geotechnical analysis and assessment of landslide susceptibility. So we were asked to provide moisture data retrospectively for a slope failure in Singapore. I can't show you that precise location because that's confidential. So I'm going to show you a slope elsewhere in Singapore where we obtained soil moisture data in the same analysis. So this is an optical image looking at the slope, and I've drawn in the crest and the toe, as you see there. It's next to a river and next to a highway bridge on the left. So we can obtain soil moisture data at the surface. We should ignore the data over the river and over the highway bridge. It's just the data over the ground that is valid and that we are interested in. So we can plot a section line through there and look at the moisture content at the surface, increasing from about 29% near the crest and to about 32% near the toe. So getting slightly higher moisture content towards the toe. So with that information, we can now perform a more complete assessment of the slope stability. So when we develop an analysis model to look at the slope stability, such as this FEA model of a section through the slope, if we know from site investigation where the groundwater level is, as shown there by the blue line, and along the surface we have the soil moisture data, and with the characteristics of the soil, we can relate that to saturation ratio and calibrate the moisture regime in the model. So with those two pieces of information, surface soil moisture content and the depth to the groundwater level, we can create a model of the moisture regime, and you see saturated below the groundwater level and decreasing saturation above, with a suitable soil water characteristic curve and running a groundwater flow analysis, we can develop this pore pressure profile. So we get pore pressure building up below the groundwater level and then suction above that level. So we can create a suction profile for the slope. So now we have effective stresses throughout the slope, and we can perform a slope stability analysis having set up those effective stress conditions. So in this example, we got quite a high factor of safety, 1.96. Doesn't seem to be any problem there. But once we have this model, we can then undertake a parametric study. How about let's vary the moisture content, because that's not a constant, is it? That varies with weather conditions. So let's vary the moisture content in the slope and see what the effect is on the factor of safety against failure. And we see quite an interesting effect there. If the moisture content were to increase to nearly 40%, we're predicting that the slope would be marginally stable. Useful information, but what can we do with that? Well, we can look at the satellite data. The big advantage with satellite data is that some of the satellites, such as Sentinel, are being archived all the time. So they have complete global coverage and data going back about 10 years. So for any site that you're working on, that data is available for the past 10 years. So that's incredibly useful as a resource to understand what's been happening at that particular site. What have the trends been? And it's much easier to interpret what's happening today if you can see what's been happening over the past several years. So we can obtain the moisture content data going back a number of years and see how much it varies due to variations in weather conditions. And we can see that over the past, over the 3 years prior to the analysis, moisture content was getting up close to 35%. So now we look at our parametric study and we see 35% corresponds with a factor of safety of about 1.5. So now we have a much more complete assessment of the stability of this slope based on data of moisture content over recent years, rather than basing it on a single moment that the conditions were measured. And with this archive data, it will be possible to look at trends. Maybe due to climate change, we're going to get more extreme weather events, and we'll see perhaps the moisture content climbing even higher. That's something that we can monitor. And with the benefit of this graph, we have an idea of that effect on the stability of the slope. We're back to the Jagersfontein tailings dam collapse, because seepage through a dam is very critical to dam stability. If you can detect excessive seepage, maybe you can detect a problem even before you start to get movement. So we tried it out on the Jagersfontein tailings dam. Now, in the post-collapse investigation, some optical images were obtained, and from those there was evidence of external erosion on the downstream face of the dam, patches of wet material that you can see in the images on the right, particularly the bottom one. So there was visual evidence of seepage through the dam. Can we detect that using the soil moisture algorithm from SAR data? So the plot at the top left, that's showing moisture content. So increasing red means higher moisture content. I've plotted the results along that red section line in the graph down on the bottom left. And you can see at one location clearly raised moisture content, probably due to seepage through the dam. And that was observed 6 months and 12 months before the collapse. So there was certainly evidence from the satellite data a year beforehand, both from the moisture data and the displacement data, that there were issues with this dam in that area. So these are all excellent indicators of the value of this data when it is used to try to avoid issues such as these. Here's another possible, or not possible, where this has actually been used, this application of the moisture algorithm for infrastructure. As I mentioned before, moisture content is an excellent indicator of impending geotechnical problems. When you have raised moisture, that is only going to lead to issues. So in the top right image, we have a rail corridor there where we are monitoring moisture content. And on that black and white plot, the lighter colors are indicating raised moisture content. So there's one particular area with raised moisture content that's plotted on the graph below, showing moisture content along the rail corridor. And that's showing data at different times. So the moisture content does vary during the year, but in that particular location circled, consistently higher moisture content. Now that's clearly a place where the owners of this infrastructure would want to go and investigate further. Perhaps there's something there that you may not detect from a routine inspection, but with the benefit of this additional information, you know what you're looking for. You're looking for a source of raised moisture content. That could be a fault in the drainage, perhaps, or a leaking water pipe, or excess irrigation adjacent to the rail corridor. You have an opportunity there to investigate and address that problem quickly and cost effectively. You could remove a potential problem even before it develops. If there was a slope here, perhaps that would eventually develop into a landslide. That could trigger a landslide. But the earlier you can spot these problems, the better. And it's possible that you could remove that problem even before any displacement develops. It could also be an indicator of a ballast fouling. So in the image on the left, okay, we're showing some mud pumping there. That would show up as raised moisture content. But ballast fouling means the accumulation of fine material in the ballast. That will tend to retain moisture. One rail company is investigating the use of this to plan ballast cleaning activities. After rainfall, we would be able to see clearly where the foul ballast is located. Now, displacement data, very useful, potentially, as you've seen. Soil moisture data, also very useful. But just the data on its own may not be of the optimum use to some stakeholders. If they see a displacement of 10 millimeters, okay, well, how do I interpret that? What do I do with that information? It would be useful to go a step further and to combine all this information and to try to do an assessment of susceptibility to geohazards by combining this information with other sources of information. And that's something that we've been developing. So we take the satellite data of displacement and soil moisture content. You can also obtain topographical information by satellite, giving you information about slope heights, slope angles, aspects, and so on. You can also obtain information on vegetation types and density by satellite data, which is often a factor in geohazard susceptibility. And we have other sources of data, such as geological maps, the existing condition data of assets, and ground truth data concerning actual landslides and expansive clay damage that has occurred, that can all be used in artificial intelligence for algorithms to learn how all the data on the left and the geological information relates to the information that we really want to know, and that's the susceptibility to geohazards. So by combining all that, we can produce maps showing susceptibility over large areas. So this is addressing the problem with the shortage of skilled engineers that we're experiencing. So these algorithms are learning from that expertise and doing that work across large areas so that the skilled engineers can investigate and deal with further those areas that are pinpointed by the broad assessment or the screening tool. I'm using that expression again. So here's an example that we used in the development of the landslide susceptibility algorithm. So on the left is the California Geological Survey landslide susceptibility map developed by conventional means. So a very valuable asset, but something that takes a long time to develop and takes a long time before it is updated. It's not a dynamic asset that can be updated readily. On the right is a model that we developed using the landslide susceptibility algorithm, and some of those areas were selected for training and validation during the machine learning process from the map on the left. The result is a map that looks similar to the one on the left. It is more detailed, so we can assess susceptibility at a pixel level. And some areas are different because it is based on the latest information. It is based on actual movement data from INSAR displacement, actual soil moisture data. It's also updated in terms of vegetation density. So unfortunately, a common problem in California is the forest fires. That can wipe out entire forests, and that can leave slopes exposed to rainfall, and that raises their susceptibility, and there have been many landslides as a result in California. That information is not updated in the static map on the left, but can be updated with the latest satellite information on the right. And that work was peer-reviewed and published in this journal, and I'm proud to say shortlisted for a ground engineering award in the UK earlier this year. We also applied it to the Auckland area. So this was a pilot study for Auckland, where they've been having a lot of issues due to recent severe weather events on landslides. So we ran the same algorithm to produce this susceptibility map, and we're working with them now to improve it based on local knowledge. Rather like the soil moisture algorithm, it can always be improved for local conditions with additional local information. So that brings me to the summary, just to wrap up. So I hope you've seen that satellites, if you weren't aware of them before, you can see that they provide a whole new and cost-effective source of data. So you can obtain ground surface and infrastructure displacements, as well as surface soil moisture content values. A big advantage of the data, the Sentinel data, is available retrospectively. So if you want to start assessing the condition of an asset or movements in an area today, you have the benefit of 10 years of archive data so that you can see how the parameters today compare with the parameters in the past. It's an excellent tool for assessing whole infrastructure networks cost effectively, so you can assess susceptibility to geohazards, pinpoint the problem areas where you can then focus other techniques and resources into investigating those problem areas. And I hope that can contribute to building in resilience to climate change, which, to bring us back to the great infrastructure challenge, is something that we're facing as an industry, maintaining our legacy infrastructure in the face of these worsening conditions. So that brings me to the end. Thank you very much for listening online and in the room.
Oh, thank you very much, Andrew. That was incredibly clearly presented. I hope you all enjoyed the information that you saw just then, because I have seen some of this before, but I thought that the way that was put together made so many incredibly good points. And I think the combination of these techniques to look at geotechnical issues was so good. Slope stability, taking into account moisture, something very difficult. But I think there's great potential. And just to reiterate that last point that Andrew made about the fact it's retrospective. If you don't know what that means in English, it means we can look at data from a long time ago. I mean, how many geotechnical engineers have said, I wish I'd put in instrumentation 3 years ago, but I didn't. Now you can actually look at that data. And I think the accuracy goes back about, it's quite good accuracy, about 10 years, is it? Yeah, so 10 years, the accuracy is of a similar level. So you get that quality going back that length of time. So anyhow, of course, we would like to see if anybody, am I doing something wrong? No. Yeah. I know that. So but before I go to the questions online, are there any questions on the floor here? Yes. Two. Well, your hand went up first. So please, yeah. Would you like to talk into the microphone? Is that okay? Okay, no, someone's coming. Someone's coming.
Hey, how's it going? So, I work in offshore industry myself, mostly with high SAS AUVs. Biggest problem is dealing with data storage. I understand that quite a lot of your data is archived. NASA, the imagery is already there. How do you deal with processing all of this data? How do you deal with storage of the data? How do you deal with computing power? That's my question.
Well, the archive data is not held by us. That is the satellite owners. So I don't know how they overcome their problems. It is an enormous amount of data, as you say. the whole world for the past 10 years. Yes, the mind boggles how they store all that data. We download the data that we need for specific areas. So it's a very small fraction of that data for each project. But for storage of data in our operation, it's a combination of servers that we have on the ground as well as servers in the cloud. So the analysis is performed sometimes on the cloud, sometimes in our own facilities. It's not extreme amounts of data that we have to deal with. We don't face the same problems that the satellite companies have with storing their data.
Actually, I have two questions. One is, you said the pixel size that you're utilizing is about 10 square meters. What's the smallest area you can come up with in terms of pixel size?
Well, the 10 meters is the average for the freely available data. So whenever we have a project, we recommend using the freely available data just to see how successful the technique is. In some situations, there may be patches of where we don't get data, perhaps in rural environments. If you do need more detail, you can use commercial satellite data, and that has spatial resolutions that range from a few meters down to even sub-meter level. But they are commercial satellites. You need to pay for the data. It's still very cost effective compared to obtaining the same data in situ. But those satellites are then tasked to obtain those images.
So that was my second follow-up question, actually. The cost of the data. Typically, you're using the free data.
Yeah.
And then screening it in some form, are you, to identify what you need for the more detailed analysis, is it? Is that how you operate?
Yeah, that's right. We would always recommend using the free data initially, rather than telling a client to go and buy all that commercial data, and then we do the analysis and we find that maybe there is always a risk that some areas they're interested in where we don't manage to get data. So if it's successful with the free data and you need the improved spatial resolution, then you can obtain the commercial data. The price varies a lot, but it's in the region of a few $100, something like that. But you may need quite a large number of images, depending on the time period that you're interested in and how big the area is.
And how many sources of free data are there? Or is it just the European satellite system or the Japanese satellite system? Or how many sources are there? And do you have to compare them?
For SAR data, there is really just the European Space Agency Sentinel-1 satellite. Recently launched is NISAR from NASA, which is a longer wavelength SAR that will be available any day now. It's been launched and they're just doing the sort of commissioning tests, and we'll have data soon. So there's not a huge number of options, but that data is available globally.
Thank you so much.
Oh, so another question. There's two questions. Can I go over here and then come back, as your table has had quite a few between you now? We'll come back. David.
Actually, my question is also in two parts. One is a question, and one is perhaps an additional piece of information. About 4 years ago, I was working on a flood management project in Indonesia on two river basins. One was the Cimanuk, which is not too far from here. The project was with the Asian Development Bank, but one of our partners was the European Space Agency, and they produced several maps. One being a land deformation map, which I couldn't understand. Being used to Landsat imagery, I couldn't understand how they got their accuracy but tonight you explained it, so thank you very much. The second part was that these maps also showed soil moisture. And as an irrigation engineer, I was very interested to see the soil moisture maps during the dry season because it gives us an idea of water management. So that seemed to be another aspect of this mapping that was useful. And then we could compare this with the vegetative index maps, which to sort of to see how they compared. So that I thought that was very useful. So the other thing is, I assume with water with water saturation, that's what you can use it as a one time. So you can see at different times of the year how the water management is being carried out. So I thought that was very useful.
Yes, soil moisture data is available from alternative sources, multispectral data as well. The advantage of SAR is that it will operate during cloud cover. So if you're in an area with a lot of cloud cover, there will be big gaps in the soil moisture data, but the SAR data won't have that problem.
Okay, I know we have one more question from this table, but I think, can you read this pretty clear? There are some quite interesting questions here. That's okay, we can see them here. It's okay, thanks. Yeah. Can you read that okay, Andrew? I think rather than me reading them to you.
Yes, okay. Question number one, can the SAR method be used for tracking coastal erosion and sediment transportation? It can be used for coastal erosion. Yes, it will detect instability of coastal cliff areas, and there are other observational methods by satellite to monitor coastal erosion, and sediment transportation when it is out of the water. And for sediment transportation underwater, there are methods of bathymetry measurement by satellite. So yes, there are certainly methods to address those. Next question. I feel a little concerned and I'd like your response. It seems that an insurance company and loss adjusters would love this data. For example, if data indicating potential failure is available months or years prior to an event, then surely there could be a shift liability for cost repair for the insurance of the consultants. Is this a correct characterization?
Whoa. Heavy question, that one. Yeah.
Heavy question. Yes, you would think insurance companies would love this data. We thought the same, but actually insurance companies, I hope there are no insurers on the call or in the room. They're actually even more conservative than engineers when it comes to adopting new technology. That's what we have found. We are trying, and we hope that eventually this data will be used more. But it is difficult. But I do agree with Jeff that there is enormous potential for the insurance industry. And the last one, thank you for interesting. I have a few questions. Typically, what is the spatial resolution of the data? With the free data, on average, 10 meter spatial resolution for displacement and soil moisture. If we use commercial data, it could get down to a few meters or even a meter. But you have to pay for the data and task the satellite. So there's no archive data available usually. Can this technology be used literally anywhere in the world? Are there any cities, countries, continents where you'll get significantly better data? No, it is literally anywhere in the world. Typically, how do you present your data to the relevant stakeholders? Do they simply have access to an online portal? Can you send data online? Either can be done. Yes, it can be presented on an online portal, a GIS platform. It's very suited to that because it's a large amount of data and it's geospatial data. So it's good to look at it on a GIS platform. But yes, it can also be provided as raw data or raw geospatial data or layers to go into client GIS platforms. And last one from Jerry, how can you be sure the satellite always follows exactly the same path? That is something that the satellite owners and operators will take care of. They do small corrections to the data due to small changes in the orbit. So they do monitor that. They do small corrections to the orbit, but there's always a slight variation between images. that information comes with the satellite image. So we can correct for that as well during our processing.
Okay, thank you for the questions online. I hope everyone could hear both the questions and the answers. I think very interesting. I must say, I had a similar question to the last one. So about, do they actually stay in the same orbit or do they move a bit?
They move a bit and they correct it.
They correct for it, yeah. Okay, last question on this table then. Yeah.
Thank you very much for your presentation. I think very interesting and impressive. So what my question is, I think maybe have some similar questions. So if we use the free data, so how can we, how much the accuracy you can achieve, like a millimeter or centimeter? And also, if we use the commercial data, so how can we assure the commercial data always get the image or save the data in somewhere? Because you say you want to access to a historic record, right? Yeah, these are two questions. Thank you very much.
Okay, the accuracy of displacement in the right conditions is about 2 to 4 millimeters. That's with the free data. With the commercial data, the accuracy is the same. It's just the spatial resolution is better. You will get more displacement points per unit area. The displacement is about the same. Same, yes. You're just getting more points per unit area.
Okay, thanks for the.
How can you get to? Because you're talking about large area analysis, But if you really wanted to narrow it down to, let's say, a house area, can it be done?
With the free data, yes, you may get one displacement point for a house, for example.
Okay.
So you're not going to get relative movement of the house. You will just get the average movement of the house. So it's not going to give you differential movement and indicators of distortion and cracking. It just doesn't have that spatial resolution.
So for a structure itself, like a bridge, it has to be a certain length to look at.
Yes, the larger it is, the more points you will get. So we have done projects with warehouse buildings, for example. And in that case, we will get several dozen points across the building, and then you start to see movement more at one end than the other. You could start to get differential movement. But for a house, it's just too small. It would just be treated as just really the movement of one block.
Okay, well, we have one final question from a Tensar colleague.
Erkan.
Hello,
Erkan.
Yeah, hi, Erkan. Right, yes, Andrew, I'm sure it's a nice and a very suitable question considering where we are in Indonesia. So very, very good. Yeah.
Is INSAR suitable for monitoring tectonic plate movements on an annual timescale? Yes, of course. Yes, I had that example from Turkey, Erkan.
Yeah, I hope you were listening, Erkan.
Yes, but yes, a very good application. And we could get vertical movements, maybe horizontal movements in the east-west direction as well. So if the fault is aligned north-south, we would get some interesting information that way as well.
Good. Okay, well, been a very nice Q&A session. Andrew will, of course, be here for a little while longer if you want to talk to him after the formal presentation is finished. I would like to thank you, Andrew, again for a really excellent, very clear presentation with a host of data, and I think maybe for many of you, some new ideas of what you can achieve with these techniques. For the students over there, maybe some interesting stuff for you to think about. You've already heard from your colleague, Alessandro, with his very interesting work, which is in a similar field in a way. So maybe there's scope there for some thesis or scriptsy, you never know. And for other engineers and people in the room, I hope you all learned something very interesting today, because I certainly did. And especially here in Indonesia, such a huge country, so many difficult geotechnical issues. Obviously, we have seismicity in most of the country, and we frequently have problems with landslides, and we have expansive soils in many places. So really, you can see that these techniques have an enormous application here in Indonesia. And I'm sure there'll be a lot of use of it in the years to come. So I'd like to bring this session to a close. One more round of applause. Andrew, thank you very much. And the all-important curry, has it arrived yet? Huh? Coming, it's coming. I hear someone say it's coming. Okay, the curry will be served in the usual way in a minute over there. Thank you all for attending. It's great to see a lovely crowd here tonight, lots of you. We have another meeting in October. There will be a notice for that one. In the meantime, please get together, talk to each other, enjoy the curry when it comes. Thank you very much.
Okay, thank you, Pak Mike, for moderating the session. And also thank you, Andrew Lees, and also Alessandro for presenting today. Ladies and gentlemen, we have now reached the end of the event. Once again, thank you for your participation. We hope we can see you at the next event. At last, good evening and stay healthy, everyone. Bye-bye.